Hi everybody, my name is Shengke, come from China, is a student in Peking University. My work is performance evaluation tool, NVMFS-IOzone. Time is short, I will pick some key points to talk about. In recent years, various NVM technologies are emerging and developing. The utilization of NVMs based on those technologies as the persistent medium at memory level is attracting more and more interesting from both academia and industry. The most popular approach is to place NVM on the processor memory bus alongside conventional DRAM, which combines the best characteristics of both technologies. The 3D endpoint-based NVM such as the Intel Optane DC persistent memory is common choice because it is mature technology and the performance is close to DRAM. This picture shows the layout of traditional and NVMe file system. There are many two types of interface for file system: POSIX, mmap. For both traditional system, high-speed page cache is used, and for the new NVM-based file system, it will bypass the page cache and block-based I/O software stack. What's more, with the mmap interface of NVMe file system, the CPU can access NVMe directly according to the mapping, which exposes the NVMe directly to the CPU, known as the DAX-mmap. Most NVMe file systems in recent years support the DAX-mmap interface, and it is likely to be the dominant interface. We know FL-IOzone is a popular benchmark tool. When we use the FL-IOzone benchmark the mmap interface, firstly allocating a main buffer in DRAM using malloc, then getting the VM address by map to map the NVMe or disk space, then initializing main buffer, moving the main buffer data from DRAM to disk NVMe by calling bcopy, finally executing Msync to keep data consistent. For both the traditional file system and NVMe file system, existing evaluation tools usually call Msync to keep data consistent, which is a standard action for traditional file system based on block device. However, the Msync will create a strawberry, which requires the operation system to find dirty pages and flash them to the NVMe disk. We use the kernel function trace to check its subfunction and the execution time. The left side of the table is execution time of the function, and the right side is corresponding function. The function filemap update write range is mainly to write back dirty pages in range. To write pages, we'll find the dirty pages in high-speed page cache and then write them to the persistent memory. It takes a lot of time. However, those operations are meaningless for the DAX-mmap because it bypasses the high-speed page cache. So, the operation system only needs flash CPU cache to write the changes to the NVMe. Luckily, Intel provides NVM libraries. We mainly two libraries in our benchmark tool. First, we check whether it is NVMe. Then we flash the data in the CPU cache to NVMe by calling PMM flash. For traditional tools, the data flow is DRAM to CPU cache to CPU, then to CPU cache, finally NVMe. Without disk I/O, the DAX-mmap can shorten the complication time of data flow and achieve low latency. For scenarios where data is only used once, if it passes through the CPU cache, cache miss will be generated continuously. Besides, the CPU cache also needs to be frequently flushed to keep data consistent. That overhead will not have significant impact on traditional file system because the disk I/O is main bottleneck. So in pursuing for even higher performance with the DAX-mmap, when data in the files are only processed once, serious considerations on bypassing the CPU cache will become a reasonable design choice. To support this potential need, we add the new data path or bypassing the CPU cache. Then the following experiment configuration, the NVM is Open DC persistent memory, the CPU is Intel, the DRAM is Micron. We take IOzone to represent the traditional benchmark tools, compare the Msync with the new NVM-lib. Except NVM-lib, except NOVA, we can find the throughput of NVM-lib are higher than with the traditional Msync. Those results confirm the effectiveness of replacing the Msync with the NVM-lib method. For NOVA, the two methods are very close. We can find out NOVA had changed the Msync behavior in its implementation, where it defines functions without those unnecessary actions. In conclusion, the overhead of traditional Msync will largely under-evaluate the real performance of NVMM file system, and by switching to NVM-lib, new tool can reveal the actual performance. Now we try the new method of bypassing CPU cache in comparison with the traditional method. The result in this picture for data used once the throughput of bypassing the CPU cache is higher than the traditional method, average 1.7 times higher, because NVM can be accessed directly and there is no overhead of disk I/O. So the overheads of cache missing and flushing CPU cache will cause significant impact on the throughput. Maybe bypassing CPU cache is meaningless for the traditional file system because the bottleneck is disk I/O. However, for NVMM file system, where bypassing CPU cache or not has a big impact on performance, so it becomes a viable technique in pursuing for even higher performance. Making it an option in our new tool can be of a big help to test those scenarios, such as the data used ones. In this paper, a new evaluation tool called NVMFS-IOzone is proposed to meet the new requirements of NVMM file system, using the NVM-lib from Intel instead of traditional Msync for data consistency, adding the option of bypassing CPU cache in the data path brought the evaluation of the new scenario for NVMM file system. Their effectiveness is referred with the physical NVM hardware. The evaluation results show that our new benchmark tool can reveal the real performance not seen by traditional tools. This is over. Thank you.
Brian Kim asks about NVM wear-out, whether wear-out or lifetime or issues are something that you looked at, and how the CPU cache bypassing affects or amplifies this problem.
Can you hear me? I can understand your question. Because my service is poor, so pardon.
Okay, so you can look at the question on the Slack channel, and I'll repeat it. The question was whether the fact that you bypass the CPU cache makes lifetime and wear-out problems bigger for the NVM.
Okay. This is a good question. I thought to compare to traditional file system, we found that the overhead of flushing CPU cache is new in the NVM file system becomes one of the main contributions to over the latency. Also, its impact on traditional file system is negligible. So in pursuing for even higher performance with the DAX-mmap interface, when data in the files are only processed once, serious considerations on bypassing the CPU cache will become a reasonable design choice. So,
Okay.
Yeah.
Thank you. I'm sorry. We have another question from Wei Su. He asks, from the figure we can see that the bypass CPU cache approach has similar performance compared with Nova. So he's curious to know about the small chunk random performance when the CPU cache is bypassed, if you have any data about that.
Okay. We know CPU cache. Sorry. Nova. The DAX-mmap interface bypasses high-speed page cache and block-based I/O software stack. The CPU can load the store NVMM directly. The DAX-mmap interface can shorten significantly the communication time of data flow and achieve low latency. So the CPU bypass the CPU cache missing will be generated continuously for sincerely where data is only used once. Besides, the CPU cache also needs to be frequently flushed to keep data consistent. That overhead will not have a significant impact on the mmap interface or traditional file system, where disk I/O is the bottleneck. However, the DAX-mmap interface or NVM, the impact of the overhead will become significant. Yeah, that's all.
So is there anything special about Nova that causes it to exhibit different performance or different performance improvements than the other file systems?
Yeah, this maybe I don't think it through. I will do the job in the future.